Understanding how and why Earth's climate is changing is a passion of mine, and something that is core to our mission at NASA. One area where climate change is already having dramatic impacts, and will continue to do so in the coming decades, is on our coasts, on which over 3 billion people live. Rising sea surface levels are making coastal regions more vulnerable to flooding. We are already seeing this in areas such as Louisiana, Florida, the North Slope of Alaska, the Maldives island chain, and Bangladesh. It is critical to understand flooding processes in coastal areas to understand predictability under various atmospheric and oceanic conditions. This is why I'm really pleased to be able to introduce this FDL project. Machine learning offers the potential for robust and reliable machine-learned surrogates for accelerating complex coastal simulators. In other words, a digital twin of our coasts.
Imagine you just bought a beach house in this neighborhood. How do you feel? Happy, right? But then a hurricane hits and flooding engulfs your home, endangering anybody that did not have advance evacuation warning. This scenario is devastating, yet unfortunately uncommon. Coastal flooding is considered one of the most significant dangers to humanity, affecting more than 1.5 million people and killing 8,000 annually. As climate change increases the rate and severity of extreme climate events, these numbers will only increase. And we want to save those lives. One way to do so is to make good flood predictions, which inform emergency response decisions, like evacuation orders. If your model incorrectly tells you not to worry, lives can be lost. If it suggests to issue an unnecessary evacuation order, trust is eroded. Accurate flooding predictions are pivotal, and we need research communities concentrating on this risk. And this is why we, 4 researchers supported by an accomplished faculty, have spent 8 weeks tackling flood prediction. I'm Konstantin, and I have a background in physics and machine learning, and you'll hear from Helga and Pesci, both earth scientists. Also, there's Nice from physics and machine learning. Now that we know why flood prediction is important, Helga will discuss its difficulty and our solutions to it.
Thanks, Konstantin. So at the present, there are physics-based numerical models that can simulate the ocean response to strong winds and low sea level pressure. They take over time wind speed, sea level pressure, and the bathymetry as inputs, and predict sea surface height or inundation height. However, running these physics-based models is computationally expensive. Due to time-consuming, today's predictions do not account for uncertainty, higher resolution predictions are not considered for real-time systems, and high computational infrastructures are needed. So that's why we need a digital twin Earth of the coast, a data-driven digital representation of the coastal dynamics that uses state-of-art physics-informed machine learning techniques and learn from the physics-based numerical simulations. Predictions with the coastal digital twin are orders of magnitude faster than traditional methods that will allow real-time predictions for a range of atmospheric and climate conditions and probabilistic simulations to evaluate risk and support emergency management and decision-making. On top of that, the models can be made location transferable, and there will be no need for supercomputers infrastructures. This makes these models accessible to other countries, some of which may not have been able to afford a dedicated flood prediction effort. We build a digital twin of the coast by predicting the sea surface height either at current time or 30 or 60 minutes into the future. We do this by summarizing the bathymetry and the forcings, wind speed and sea level pressure, at the current time and up to 15 minutes in the past, in 5 minutes intervals, as multi-channels image. We are using this as input to our physics-informed computer vision model. The sea surface height itself is hard to measure, and it's not provided as an input to the model. Now I will pass to Pishi that will talk about the results that we achieved.
Thanks, Helga. So here are our results in developing a surrogate model for Nemo Ocean using Fourier neural operator, which is a physics-informed deep neural net that leverages Fourier transform as a low-pass filter to learn the dynamics in the frequency domain. We use UNet, another deep learning model using convolutional neural net, as the baseline for comparison. From the left to right are the animations of the Nemo simulation, FNO, and UNet emulation for present estimation on sea surface height. As we can observe from the animation, FNO generally reproduces the true dynamics, particularly for the trend of sea surface height over time. By comparing FNO and UNet using skew metrics, a mean square error, and structural similarity index, we found that FNO outperforms the baseline UNet. Also, note that using FNO, we can achieve hundreds of simulations in the order of minutes, which is magnitude faster than the physical model. Now passing to the results of the present and future estimation using historical dynamics up to the previous 15 minutes with mean square error plot shown on the right. First, FNO, which is the orange line, outperformed UNet, which is the blue line, for all the cases in predicting the current time step in the next 30 and 60 minutes. Further, we also observed an increase of mean square error over future time for FNO, indicating a potential divergence phenomenon when the predicting time step gets larger, which is still reasonable in this case, given that the mean square error is much slower than the UNet baseline benchmark. Also, note that the results were achieved with only a single run because of the limitation in time. With that said, more improvements can be achieved in the future. Now I will pass to Nis to talk about our platform and future work.
Thanks, Pishi. Now that we have created the first digital twin to improve flood predictions, we want to empower others to do the same. The main contribution of our work at FDL is that we have built a platform to enable the development of machine learning associated surrogate models called coastal twins. It provides an extensible way to integrate simulations from physical models such as NEMO and Cosmos with machine learning models to produce reliable, accelerated emulation of coastal ecosystems. In addition to the tasks specific to this project, this platform will further foster collaboration between machine learning and earth scientists, speed up progress in coastal surrogate modeling, and be adaptable to similar surrogate modeling tasks. We achieved a lot during the last weeks, and we're already planning the next steps. First, after doing more thorough experimentation on NEMO, we will run our surrogate model on other physical models describing different regions of the world. Cosmos, for example, is a high-resolution, multi-scale model on the US West Coast that would hugely benefit from a surrogate model. Here, we can train on one geospatial location and apply this model to another location of the world, disentangling the physical dynamics from the concrete geospatial location. Secondly, we see our work on the frontier of a research domain which is currently dominated by solving differential equations numerically or shallow neural networks on the machine learning side. As far as we know, we are the first to develop cutting-edge physics-infused machine learning techniques to complex, real-world coastal systems. And it is important to continue extending our portfolio with more machine learning models, pushing both machine learning and earth science communities. With our current code base, we have laid the groundwork for interesting, valuable applications, such as uncertainty estimation, where the likelihood of certain outcomes of the simulation can be inferred. These and other improvements we will continue with research partners and deploy to the open source repository very soon. As confirmed by the latest IPCC report, ongoing climate change will result in more flooding and droughts. While our project does not prevent climate change, it helps to adapt to a world with more severe climate events. Currently, high-precision physical models are too slow to run in real time. In the future, with digital twins, precise, uncertainty-aware, life-saving flood prediction will be commonplace. So let's fight climate change and build on this work to improve flood predictions using machine learning.
Thank you very much, Digital Twin of the Coast team. Such important work. And I'm going to bring up Bill and our panel.
Wonderful. Thank you, Sarah, and thank you, team. Fantastic work. And of course, it couldn't be more timely together with the other two Earth Science projects done by this year's FDL teams. So joining Scott and I to talk about this work is Dava Newman, who is a professor of aeronautics and director of the MIT Media Lab. Also, previously during the Obama administration, was the deputy director at NASA, and most importantly, is an incredible member of the Board of Trustees here at the SETI Institute. So welcome, Dava. Thanks for joining us. And let's start with you.
My pleasure.
Can
you hear me?
Yes, we can hear you. What were your what are your reactions to what the team did and the promise that this kind of work holds for the future in terms of flood and other natural disaster predictions related to climate change?
So congratulations, team. That was amazing. I have a whole list of questions. So first, I'll just give you kudos. I loved your talk. We'll get into the details, I'm sure, with some questions, but my hat's off because you went after the hardest question. And those are the kind of questions we like, to make the digital twin, and especially to really hit the physics. I'm biased, I am an aerospace engineer. So, and I love that you talked, about bridging the gap. That's what we find in our work. Of course, we have amazing climate scientists. We have amazing ML, AI folks. But the whole goal is to get you all working together. And it looks like this team is a big success. So my hats off to you. I do again have questions. This is really important work. So my questions are kind of future thinking too about what do we do next. You mentioned other models that you think it'd be applicable to right away, because I would actually love to see this scale, right? As soon as possible, or continue working with this team, whoever wants to. It's just such an important contribution to get these physics informed. And I do have some questions on your Fourier analysis as well, but I'll leave it there, Bill, and take maybe some of my technical points offline and let us go around the squares here so we can all have time to talk to this incredible team.
Great. All right. Scott, your takeaways here. I mean, to what extent do you see this kind of work of digital twin being applied to not only things like coastal inundation issues, but all the other issues we're seeing related to climate change in terms of drought and fire, extreme weather events, et cetera? I mean, what's the potential here?
Well, I think, Bill, I'm really encouraged by this result. I mean, we've for years have been working on AI. We want to use it as a tool of science. And what we're finding now is that we're with projects like this, we're starting to see, and you're really working through, how do you actually use AI in science? And it's in the sense of, by making these predictions, you can sort of do a low res, scan across a much broader area. And then the AI makes a prediction. And like some of the other friends at NASA treat AI as an idiot savant, saying, I don't know what's going on, but there's something interesting here. And now that becomes the hypothesis for the scientific method. I think that idea of iterating between AI and science and these, what you call the digital twin, is the future of science in my heart. But it takes folks and leaders like you to actually show us the way. How does this actually work? And how does it validate? And how do you answer Dava's questions? That's what I want to know. Right? And as you go through that, because I think this, to me, is you really pushing the forefront to me of science, like we did recently with the protein folding and understanding how proteins, in deep mind. This is advancing in a very important area that matters for everybody on the planet. So thank you very much for your work. It's fantastic.
Yeah, wonderful. Dava, just before we jump to the next team, what are your thoughts? I know you have lots of questions that we'll have to work with you offline with the team to address, but what is a quick thought on your part of what you'd like to see next? What's the next stage of development in the work that the team that did this year from your perspective?
Thanks so much, Bill. So I would say, the generalizing it and to capture other models. Use the IBM's NeMo, that's great. But, the trap is everyone says it's only good for that one model. Show me how you mentioned, if it's generalizable to this model, because you want to ingest and work with the existing climate models. And then you decide, this is how I can show you how I've really sped up my calculations, because that's what people care about when they're in harm's way. We're in a flood or fire. We have minutes to
Yes.
not even hours to get people out of harm's way. So if we could generalize it to using a little bit more in terms of different models, you would convince people. That's what I want you to. I want you to convince the world, not just me, that we can do this. This is generalizable, and those use cases are really important. So maybe a few more climate models, making sure that the uncertainty. I know we don't have much time, but the uncertainty analysis is key. So you've done great, but that's a really hard problem, and you're at the forefront. So the other thing is I want to see you all publish this because that's what you should do.
Yeah, absolutely. Well, it's certainly about speed, about better predictions, and about, more time and more reliable predictions. So that's fantastic. Thank you, Dava and Scott, once again.